Good morning, good afternoon, good evening, good wherever you are. Thank you for joining the SNIA presentation about cryptocurrency and computational storage. Today, we're going to have John Michael Hans from Chia Network and myself, Ellie Tiomkin from NGD Systems to talk about cryptocurrency. But before we jump into the body of the presentation, a few administrative items. First of all, the legal mumbo jumbo. We're not lawyers, no warranties, use at your own risk, all of the above. And a few words about SNIA before we start. So, what is SNIA? SNIA is a nonprofit global organization putting all its focus on standards around storage and network. Over 2,000 active contributing members, 50,000 IT end users around the world. Under SNIA, we're part of the CMSI, which stands for Compute, Memory, and Storage Initiatives. The CMSI has three main areas of interest: computational storage, persistent memory, and solid-state drives. We're obviously under the computational storage, and the computational storage does have the technical working group and the special interest group that focus all around the industry standard around computational storage and creating awareness. On today's agenda, we're going to talk about what is cryptocurrency, what are proof of space and time, what is computational storage from a high-level perspective, and how they're combined together and what's the value. So without further ado, John Michael, the stage is yours.
Hey guys, this is JM, VP of Storage at Chia Network. Today I'm going to give you guys a quick overview of proof of space and time and some concepts we have in the consensus called proof of space and time. There's stuff like plotting and farming, and we'll kind of walk through how these proofs of space are actually generated, which is really interesting. The first question is like, why storage? We have Bitcoin today that uses proof of work. And I think everybody knows now that at least proof of work has got a bad rap for consuming a massive amount of electricity. When Satoshi Nakamoto wrote the original Bitcoin white paper, they had this line in there called one CPU, one vote. But the whole idea in the white paper was basically to take this underutilized resource. At the time, there was free CPU cycles laying around, and saying, okay, couldn't we use these to perform some work and basically put together these blocks in a blockchain that can and use proof of work as this thing that they called Nakamoto consensus to basically prove to trust in an untrusted system. So this idea of Nakamoto consensus is basically decentralized and permissionless access to a blockchain, which means you don't have to trust anybody. You just look at the blockchain, look at the chain that has the longest number of blocks, and you can trust that one. So this idea actually works in storage. In storage, we'll talk a little bit about why it's such a really good resource for this. But the first is that the storage is a commodity market. It's large market. The NAND market, something like 53 billion last year. The hard drive market, about 22 billion. The SSDs, I think about 35 billion of that NAND market. So it's just, these are massive, giant, growing commodity markets. IDC put out a paper a little bit. It was like early last spring, kind of during the craze when we launched Chia, but about this hypothesis about this underutilized storage. So IDC was super excited about this report that they wrote for us. We worked with them because they had all this data on how much storage is underutilized. They have this like age of the data sphere report. I think at the time of last year, it was like 6.7 zettabytes of global storage install base. The hypothesis was like, wow, there's probably about 500 exabytes on consumer hard drives and consumer desktops alone, just hard drives of underutilized space, meaning that the average desktop user is only using about 30% of their hard drive. So this is a cool opportunity for this idea of like, okay, there's a stranded resource. Can we take advantage of this to use for cryptocurrency to secure the network? And if we can do that, we can do it in a way that's much more energy efficient than doing proof of work. And the idea is that with proof of space and time, you do the work once up front, and this is called plotting. This is what we're going to talk a lot about today. And then you store it on non-volatile memory. Everybody knows that non-volatile memory is super power efficient, right? You turn off your phone, you turn off the screen, and you shut your laptop, and your battery doesn't die. and your data doesn't magically go away. This is why it's called non-volatile storage. It's not volatile when you turn the power off. So you can store user data at zero idle power and have very quick access to that data. It's a problem we've already kind of have the solution to in the storage world. And so this is really exciting because if you can take this underutilized resource of storage and now use it for cryptocurrency, you can have all the security that Bitcoin has. You can have this true Nakamoto consensus where you trust the longest chain. But today you're using 1/600th of the annual energy usage of Bitcoin. So, you can basically have your cake and eat it too. You get all the security and you get low energy use. And there's been a lot of talk about e-waste and scope 3 emissions, and there's a lot of focus on sustainability. I've been working very closely in the Open Compute Project sustainability work group on some of these things like circularity. Late last year, we announced this thing called the Circular Drive Initiative with Bill McDonough, WD, Seagate, and Chia about kind of incentivizing the circular economy for storage devices. And there's a large opportunity here because there's a lot of data security risks in storage sanitization. At least there's a perceived risk that companies basically, when they're end-of-lifing storage, basically are destroying or physically destroying that storage. Well, there's a great now opportunity to use that for applications like storage-based cryptocurrencies because they don't store user data. So there's not like a lot of data security risks when you're putting just random cryptographic data on the drive. The other thing is that there's no durability requirements or error, like uncorrectable bit error rate requirements for the use in these types of applications, or it's very low compared to like, for instance, actual user data, because if you do lose data, you can just recreate it. So it's not catastrophic. So there's a huge opportunity now, not only to just say, oh, we're preventing the e-waste from application-specific integrated circuits like Bitcoin miners from being used, for while they're efficient and then being tossed into e-waste, but there's actually an incentive to basically take drives that would have otherwise been destroyed and use them for Chia farming, so and other applications. So there's a huge opportunity here in the sustainability aspect as well. So in Chia, we have this thing called farming. It's not called mining. We don't call it mining, and a lot of people are off put by this. But it's proof of space and time is very different than proof of work. So you do these cryptographic hashes and you store them in a file. We call these plot files. And we'll talk a little bit here about how those plot files are actually generated and how they're put together. But then you get challenges that come in on the network, and you can think of these plot files like bingo cards. You basically, as a farmer, when the challenge comes in, you scan your plot files and say, do I have one that is close enough to that challenge? If I do, I get to form the next block. I put all the transactions that are in the memory pool, mempool, into a block, and I form the next block in the blockchain. And if it meets the requirements of the challenge, I can basically get to Chia as a reward. So now you're incentivized to basically put your storage up to the network, and your hash rate or your power of the storage on the network is basically how many terabytes you have, and it's proportional to the total net space, which is the total number of storage that is being used in Chia farming. So it's very easy to look at your rewards. Just the more storage you have, the more you win, and it's kind of like that. So what we say proof of space and time, proof of space is really the star of the show, because as I mentioned, proof of space is dictating, how much power you're giving the network. But we have to have these things called proof of time in there too, which is this verifiable delay function. So there was two pretty major breakthroughs in mathematics primitives to basically make proof of space and time work, which is why it couldn't have been done for some of the early implementations of storage-based cryptocurrencies weren't successful because they didn't solve all these problems. So for one, the proof of space, it's called a proof of space. You have to prove to the network that you're storing a certain amount of data. This is the proof of space. And so you want to be able to do this quickly and efficiently. You don't want to waste a bunch of IO resources, basically proving that you have the storage. Obviously the easy way would just be like, okay, give me some random LBA. And how do you verify that that's you're actually storing the data? Well, we have this really nice proof of space primitive that basically allows you to do this quick, efficient verification of hashing functions and matching to basically prove that you're storing the data by only doing a few IO requests. This is really awesome. The other thing is it needs to be resistant to attacks. There's obviously attacks in proof of work is like this. Everybody knows this majority attack where you have a 51% of the hashing power. So those types of same attacks exist in Chia. And so the amount of space you have total on the network actually provides more security on the network. The other part of this is called the verifiable delay function. This is another primitive where Chia is the first blockchain to actually implement these VDFs in production. we basically there was a lot of mathematics behind this verifiable delay function based on this performing of squaring of computations within class groups of binary quadratic forms. And this is one of our most cited papers. But what this really means is it's a workload that can't be parallelizable. You have to run it in serial. And the number of iterations that run from the squaring is an easy to verify output. You have a succinct and compact output that's canonical. And so you need these to basically put on top of the proofs of space to prevent something called a grinding attack. So I'll talk a little bit more about this, but basically the proof of space, the proof of time is basically there to secure the proofs of space so that people can't do these weird long range attacks. But verifiable, again, it means after performing the computation that you prove that you took some amount of time to take it, and the prover can do that very succinctly. They can verify that. Delay means you actually spend some amount of time doing that. And then function is that it's deterministic in the output, that X input always equals Y output. So if you think about, like, I don't know if anybody's familiar with Bitcoin, of how like the protocol works in Bitcoin, but basically, you take the previous header of the block and you hash that with SHA-256 with a nonce until you get an output that is lower than the difficulty for the epoch. And every 2 weeks the difficulty in blockchain in Bitcoin is reset so that the block time is on average 10 minutes. So the obvious proof of space is just to perform these hashing functions and then store them to disk, write them to disk. That's broken, because if you think about it, you can just say, like, well, if I run my hashing function for twice as long and then write it to disk, I have twice as good of proof, or twice as good a hash. Or if I want to run it 100 times longer and then store it to disk, I could have a proof that's 100 times better. So there's a name for this. This is called a Hellman attack. And this is a time-space trade-off where you can basically input more energy and compute up front into making a better plot or a better proof. So the way that Chia alleviates this problem is by using these plotting tables. So a plot, or the like kind of unit of security for the proofs of space in Chia, is this 100 gigabyte file, and it's broken up into 7 tables. And the first table is these pseudo random hashes that land in these random buckets, and then the tables 2 to 6 are basically back pointers that have these entries in these tables and back pointers to them. And then each of these tables have 2 to the k entries in the table, and then this kind of determines the plot size. So in Chia, we have this k equals 32, which is the minimum size requirement for the storage on the network, which happens to be 101.3 GIB or 108 gigabytes. But you can basically use this function to basically determine the size of the tables. So again, the reason why plotting is challenging and hard is because you want to make this proof of space very easy and verifiable. So once we get to the farming part, which is actually doing the work on the network to secure the network in Chia, then now it's very easy. You can do a proof quality check where you just pick a random proof in table 7, and then you just all you have to do is 9 read requests, 9 IO requests, and then you can see if you can have a valid proof that meets the requirement of the challenge. If you do, then you have to do 64 random reads to basically verify that and form a full valid proof that you can send to the network. But this is a very, very small amount of IO. I mean, anybody, I'll talk a little bit more about the farming workload, but the whole idea of plotting is to make it very, very easy and quick and efficient to verify later, because the plotting needs to be done once, and then you can farm for many, many years. You can farm for, say, 5 to 7 years after creating these plots for a single time. We earlier in the year, I know there was a lot of discussion about SSD endurance, and I wrote a couple of blog posts on this. But plotting is a write intensive workload. When what you're doing is you're laying out these tables, and this phase 1 is the forward propagation, where you're basically doing these. We use Cha-Cha and Blake 3 as the hashing functions to lay out these tables, and then you forward propagate these into all these tables. You find this cryptographic function where you match the entries in the table. And then you do this back propagation, which removes the entries that didn't form matches. And then you do this compression, which is trying to basically it's algorithmic compression. You're looking at the pointers and trying to find the most optimal way to store all those. But there's a lot of sorting on disk. Like what this plotting looks like is just a lot of IO, a lot of CPU, a lot of DRAM, because there's a lot of in-memory sorting that's going on. So today, each k equals 32 plot takes about 1.43 terabytes of disk writes. So, for a data center SSD that say has like 40 petabytes of endurance for sequential endurance at a writing up of 1, this is nothing. This is like not very much. But for consumer SSDs, it's kind of a lot for one workload. So, some of our initial recommendations for Chia was like, don't use consumer SSDs. Now, a lot of people use consumer SSDs because that's what they had laying around and found, oh my gosh, like you can go way, way beyond the TBW rating for some of these consumer SSDs before they break, which is not shocking because they have to rate them at kind of these worst case write amps for JEDEC. And also the NAND is actually much capable. And even when you run out of endurance for some of these consumer drives, they're finding out that really the trade-off is retention. So, but there's better ways to do it, right? I think people figured out if you can basically get 110 gigabytes of RAM and cache that, you can cache about 72% of the writes and reduce the writes just by having 110 gigabytes of DRAM. But now you have to do this offloading from DRAM back to disk. And if you have 416 gigabytes of DRAM, you can do this entire plot generation in memory. You don't have to touch disk at all. But for obvious reasons, this is quite a bit of this is quite a bit of DRAM for like a consumer system. This is like well beyond high-end desktop space. Now you're into the server space. So no, it can be done with lower amounts of DRAM, but that requires some space trade-offs, like increasing the capacity by a little bit. So that's not good. So plotting happens to be really fun. And part of the reason why I got into Chia, it's just, it's really fun because it's kind of like a all-around benchmark for a system. It's like one of these really interesting workloads where you're tuning the IO to the CPU cores into the memory bandwidth, and everything matters. And if like your CPU is not going fast enough, then you're going to pull down your plot time. If your CPU frequency is not sustained, then your plot time is going to be impacted. If you're getting IO bottlenecked, and we call this IO weight, then that's going to bring down your plot time. So the thing that matters most in plotting is one, we do a lot of disk writes. So what you need is, obviously looking at a high endurance SSD is good, but you need an SSD that can also sustain a large amount of write bandwidth, because you don't want to slow down the CPU. If you're not writing fast enough during this sorting, then you're going to be slowing down the CPU and waiting. So the whole idea of plotting is you want to plot as fast as you can because you want to fill up the hard drive. But once you're done with plotting, you basically just copy them over to a hard drive, and they just sit there forever, idle. So once you can see here, this is kind of just like a little picture of the GUI where you can select your K value. So you can do plotting from the GUI, or hardcore people are doing plotting from the command line interface. And there's different plotters that the community has written that have different attributes as far as like memory use and storage use and resources. But yeah, once the plot is done, this is what it looks like. Just it's a 108 gigabyte file. You can see 106 million kilobytes. This is it. And so plot is just it tells you the plot size, the date, and then the plot ID, which is just a hash of the plot public key that was made to generate the plot, and along with the farmer key and the pool contract address, which is part of the things that the public keys that identify the plots. So the plots are unique. But when you win and you find a proof of space that's valid, you have to sign that plot proof with the actual private key from the plot. So it's important that the farmer has access to the plots. Now, what the final plot, like what is even in this 108 gigabyte file? It's just a bunch of random cryptographic data into these tables. And you can see here, I've kind of sorted out like this. One is this first table, this red is the second table. You can see they're all about 15 gigabytes in size. These last tables are, I think, about 17 gigabytes in size. But this is what a plot looks like. A bunch of, it's 2 to the K entries per table, and there's 7 tables, and then there's a lot of random hash data into those tables. So now the topic of today, how can computational storage help speed up plotting? So one, I think you got from the beginning that proof of space and time is absolutely revolutionary. There is only 3 consensus mechanisms that are viable in cryptocurrency today. One is proof of work, which Bitcoin and Ethereum use, and it's been had the longest tenure of cryptocurrencies, and as far as solving the problem of trust in public blockchains. And then there's a lot of people that are using proof of stake, which Chia believes there's lots of problems with, but proof of stake means you're basically staking coins, and people that have the most access to money will have the highest number of rewards, so kind of incentivize the centralization. And then you have proof of space and time. So we really, if it's not clear, we think it is going to be a massive impact on the industry, the storage industry, and in the crypto industry in the next coming years. Like when people figure out how important this is and how revolutionary it is, when you can have the security of a public blockchain like Bitcoin, but have the energy use of something like proof of stake. It's really, really exciting. So I think there's a huge opportunity to basically be able to speed up this plotting. So one is, this compression is really hard. Again, it's algorithmic compression. You're trying to like compress back pointers into more compact formats and these stubs and deltas. You can read up all about our plot format if you're really interested in all the codes on GitHub and all the documents that outline our plotting. The Chia proof of space construction is released in papers. There's a couple really important papers that got released on how this is done. But this is not just for use in Chia. Any cryptocurrency now can use proof of space and time, and we will likely see hundreds of cryptocurrencies that use proof of space and time in the future because of how powerful it is. The other opportunity I mentioned, there's lots of sorting on disk, and so there's probably a computational storage edge where you can do acceleration of that. Right? If you know how to do this algorithmic sorting, and you can do some of these hashes on the disk itself, and with the CPU on board, then you can probably save a lot of the sorting that needs to be moved. As you saw from the screenshot I had, a lot of the plotting right now is just moving data back and forth between DRAM and disk to sort it. And it's a tough problem to solve from computational storage, not only because it's just a hard technical problem to solve, but there's an economic problem, which is like, you have to beat all these. Everybody is trying to do this very inexpensively and fast. So you either have to beat the cost of high performance SSD, or you have to beat the speed of DRAM for a better TCO. And so there's lots of opportunities here, but it's not just a technical problem. There's also a kind of economic incentive. And so there's certainly an opportunity to reduce the disk writes. If you're doing the sorting on the disk itself, then there's a huge opportunity to not have to move that data back and forth between host memory and the disk. And I think we have a very interesting use case today about an opportunity for low power plotting with an onboard compute in a computational storage device that we may hear some about here in a sec. So just, I'm pretty much out of time in my section, but I'll go through these last couple. What does plotting look like today? Either you buy a server, a workstation, a desktop, and you kind of add an SSD. And again, you kind of want fast cores or a decent amount of cores because you take CPU and DRAM, and you need this temporary storage. But the problem with this approach is that you only need the plotting hardware for when you're plotting. In Chia, this is typically a month or 2 months, maybe 3 months, and then the next 5 years to 7 years, you're just farming. You just have the hard drive sitting idle. So you have to go figure out that hardware after you're done plotting. There's other now providers that are doing plotting as a service. Of course, you can do AWS, but as people found out with AWS, when you're downloading 100 gigabyte files, AWS egress is not very nice to that, and it's very expensive to do. So now there's new services. There's one called Akash that's interesting. That's like a decentralized plotting as a service based on a cryptocurrency. It's kind of like the AWS of crypto. So there's really good opportunities now for plotting as a service too, especially as proof of space and time becomes more popular with many other cryptocurrencies. The really important thing is that the whole idea of this plotting is to make it really efficient for farming. Once the plots are sitting on the hard drive, I mean, this is the easiest workload ever for a hard drive. It's 0.4, 0.5 IOPS. The hard drive is idle 99.7% of the time. It requires 2%, 1% of a 8-core system. I mean, this is like no CPU cycles at all. So this is the magic. Once the plots are on the hard drive, they just sit there, and you can secure the network and do these cryptographic bingo cards with the plot files, and it's like almost no energy use. This is really exciting to get into SSDs, because SSDs can go to sleep or go into very low power states and go resume with just a couple hundred milliseconds of latency from a zero idle power state. So you could theoretically do farming with zero power, which is super exciting for the future of farming in SSDs. And I know we're economically not there just because of just the cost of disk is very low compared to SSD today. But we are in an interesting point where if you wanted to know, like this is how people are farming today. Basically, they're taking JBODs or NAS and putting high capacity drives in there. But the way you measure the efficiency of farming, right? You're trying to store the most amount of data in the smallest amount of space at the lowest power. If only we had a metric for this. Oh, yes, we do. It's called the total cost of ownership. And you can use the SNIA total cost of ownership calculator on SNIA's website to calculate this. This is an example I have just of like how you would break this down. Using high capacity disks in Chia impacts the TCO because you're amortizing the storage and the plotting hardware and the JBODs and all the other stuff in the rack. You're amortizing that over more capacity because in Chia, all that matters is how many terabytes you have. This is not dissimilar from archive storage. It is not dissimilar from other types of storage applications. So I think the TCO understanding for Chia is a really good case study for how to do this breakdown in other storage applications, right? You're looking at the CapEx, which is the amount of capital expenditure or how much money the storage costs. And then you're looking at the OpEx, like how much it is to run that storage. And typically the OpEx power, the OpEx is dominated by like power and rack space and cooling. But, it could be other stuff like drive failures if you're using different types of drives. So I think Chia is a very, very good case study for understanding the total cost of ownership. A community member actually wrote a really awesome model based on the SNIA TCO model. And I kind of helped give him some input, but it's here at chiacalculator.com/ROI. But this actual calculator is like better than 99% of the calculators I see on like storage companies' websites. It's very, very good and well written. So if you guys should check it out, but it basically uses the math in the SNIA TCO model to basically do this calculation of like how much per terabyte are you spending on hardware acquisition costs versus OpEx and power and cooling. And it even tells you like you can put in prices for Chia and tells you how much you're going to make over a couple of years, whatever. So very, very cool. Check it out. And wow, I know that was a lot to go through, all things plotting and farming here in just under 30 minutes. But I'm going to hand it over to Ellie to talk about computational storage in Chia.
All right, thank you, John Michael. So now when you all are experts on Chia and proof of space and time, we'll try to touch a little bit more on the computational storage side of the business. So the idea of bringing compute to storage has been around for a long time, but we really seen it coming to fruition and started grabbing attention in the last few years, and that's where SNIA adopted the technical working group for computational storage. And one of the main drivers for that was the appearance of NVMe SSD. So NVMe enabled really high efficiency, high performance from the NAND. And with that came a few startups. Now we also have a few large companies that are offering computational storage solutions. In this presentation today, I'm going to focus on the computational storage drives, where it is an actual drive that adds a compute capability. If we look at the infrastructure of the compute storage network as it is today, the traditional one, then we have a CPU, a GPU, we have the memory, and we have the storage. Well, what's the problem? Why do we need computational storage? Where did the need emerge from? Well, as we store more and more data, we create a mismatch between the storage and the network and CPU capabilities. There's too much data to move from the storage to the host for processing. And the problem is just going to become more severe as we accumulate more and more storage. And you all seen the Gartner and IDC and all the research companies with, gazillion storage growth over the years. And computational storage is here to try and alleviate some of that pain. It's not here to try and replace the host CPU, but it's here to augment it and take advantage of distributed processing. So you take that compute function that was traditionally done on the host level, on the CPU or GPU, and now you run it on the drive level. So every drive have a compute core that can run either a storage function like compression, decompression, encryption, or non-storage items, any type of application or container, image processing, video analytics, database, whatever it is, and run it locally on the storage. Now, obviously, the core that you have inside the computational storage device, the CSD, is much lower in terms of power from the host CPU, But it's not a problem because you take advantage of distributed processing. So you have many drives or computational storage drives in the server or in the rack, and each one of them is doing a small part. But when you add them together, they contribute much more than the very powerful host CPU or GPU. And the main thing that they provide is the elimination of data movement. Today, nobody's really measuring the time and effort and inefficiency to move data from the storage to the host for processing. When you have an application that you can run in the storage where the data reside, now all of a sudden you don't need to move all the data back and forth in chunks from the storage to the host. And that's the real magic of computational storage, enabling the workload in the drive. And it can be the same type of application that the host is running, or it can be a completely different type of application that just doing the initial screening of the data and let the host do the heavy lifting of processing. So there are a lot of ways to implement computational storage. The benefits are mainly around faster performance, lower power from a system perspective, and increased efficiency. So now that you've done the crash course on computational storage, let's go back to our topic about cryptocurrency. John Michael provided a very good overview of what's the proof of work, require CPU or GPU effort versus the proof of space and time that requires storage. Well, computational storage devices are storage. So how can we combine the two? We can enable the actually plotting that the host is doing on the drive level. So think of a server, a 1U server or 2U server with 24 slots of UDA2 NVMe SSDs. On a traditional system, you have the host doing plotting with a 24 super fast NVMe SSDs, enterprise grade, that generate the plots. And when the plots are ready, you move them to the hard disk drive for farming. But now, what if each SSD, each one of those 24 SSDs, can run the autoplot? Well, that's where the value is. And the way it can run the autoplot, each SSD has its own operating system, very seamless programming model, enables to take the plotting algorithm and just drop them inside the drives and have the 24 drives plot in parallel on top of the fact that the CPU is now plotting. So the outcome is you get much more plots in a much shorter time span, so higher efficiency. Yeah. John Michael did mention the SNIA calculator, and here's another example. And this one compares system based on this is a rack level TCO calculation per terabyte, and it compares HDDs, SSDs, and computational storage SSDs. And you see that computational storage SSDs do provide the highest efficiency level. And it's not only the ability to run the Chia on the plot as a computational storage service, but also the capacity of the drive. So one of the drive is 32 terabytes. On $1 per gigabyte, you can compare it to an HDD. But if you have a whole rack filled with 32 terabytes, it's probably equivalent to 4 or 5 full racks of HDDs. Now you calculate the cooling, the space it captures in the data center, the power consumption, and all that is getting added to the actual calculator and providing higher value on CapEx and OpEx. Here I have another snapshot of the actually Chia GUI that demonstrate how computational storage drives are actually plotting on top of the host CPU. The GUI is very friendly. If you haven't tried it and you're considering plotting and farming, it's going to be a very easy experience. Also, there's a lot of YouTubes out there that will guide you step by step how to do the process. So how much are we saving? If and this is based on a 2U server with 24 32 terabyte computational storage devices. that are running the autoplot. And what you see here, you see at the red, right? It doesn't matter how many drives you add to the server has a certain limits on how much it can plot. And that makes sense because there's a CPU, there's storage, and the CPU can only plot at a certain rate based on the network, how much it can communicate back and forth to the 24 drives. And bear in mind, these are NVMe enterprise grade, extremely fast SSDs. On the green, we see the computational storage devices. So the more devices you add, the more plotting capability that you add to the system. Every CSD has its own core for plotting. It's the concept of distributed processing, just like working with the minions, right? You have so many minions, and each one of them is doing a little bit, but when you add them together, they're as a whole, they contribute much more to the system than if you just rely on that one master, one CPU. And if you'd like more details about actually how we got to this calculation, we have some white papers and explanation that can provide further details. So that was the last slide. Thanks for jumping on the webcast. I hope you find it insightful. We still have some time for Q&A. So if you have questions, just write them in the Q&A or chat window, and we'll be happy to take questions.
Yeah, and I guess I should have mentioned when we were talking about the SNIA TCO calculator, we did put a link to that in the same webcast link that's here in the announcements. And I just recorded a new video that hopefully is up, kind of walking through the spreadsheet model of just how to do it, how to walk through a TCO case study. But again, this is really useful if you're doing anything in storage, if you're doing durable storage, like say it's Ceph or an object store or any kind of interesting TCO calculation. The TCO model is very useful. So this hopefully you can use the cryptocurrency as kind of a case study for how that works. But so
okay, John Michael, there's I see then the question. So the first question is, you mentioned that proof of space and time is more energy efficient than proof of work and similar to POS, I guess it's proof of space. How would it compare to proof of authority, which has also been said to be one of the most energy efficient consensus mechanism?
So there's no free lunch, right? Proof of stake will try to basically say, oh, we're as secure as proof of work, but with, like taking zero energy. So there's no free lunch. Like obviously there are hard drives and they consume a small amount of electricity and they're, hundreds of times better than proof of work, but it is more than proof of stake. So the whole blockchain trilemma is if you don't have a secure blockchain, then the power consumption doesn't matter because you could just do it in a Oracle database or an SAP or some kind of centralized database. If you don't have a public aspect of the blockchain that uses Nakamoto consensus, which means it's permissionless and decentralized, then arguably the power consumption and things aren't as interesting. So that's one of the things we believe strongly in, and I think we've shown that proof of space and time, because that barrier to entry for plotting and farming, it actually is pretty low, right? Because then you just basically need a desktop and a hard drive to get started. And then once you're farming, you can farm off of a Raspberry Pi and a hard drive. There's over 200,000 full nodes for Chia right now on the network. So again, we expect proof of space and time to be much more decentralized and much more secure than these proof of stake alternatives. And so it's tricky to compare, all these different types of blockchain consensus mechanisms. But, again, really, they all fall into one of these categories of proof of work, proof of stake, or proof of space and time.
Yes, there was a comment at 9 minutes into the talk. Someone asked if we can slow down. I'm talking too fast. I guess too much coffee in the morning. Sorry about that. But if we did talk too fast, you will get a link to the recording of this webcast. And in the recording, you'll have full control on the play and pause. You can pause after every word, sentence, paragraph.
I have a few too many slides, but I'm certainly happy to come back and talk more about some of these, like each one of the specific topics I talked about, deserves a 1 hour talk, right? Like, I couldn't do our verifiable delay function justice of like how awesome the math is. And I'm still, as I'm a storage guy, not a mathematician or cryptographer. So that stuff is like way over my head, and it's like drinking from a fire hose. So I'm having a lot of fun learning all these, primitives.
Yes, another question for you, John Michael, and then a question for me. So, can you compress dedupe compact plot files?
Yeah, so the problem with there is like right now in the current G implementation, there's about like 1% you can do if you do a C standard or some kind of like regular compression algorithm, because there's like a small amount of padding between the plots so that there's some alignment. But like, no, I mean, it's random data. You basically, in the entries in the table are the output of like a Blake3 or cha-cha hash function. So I mean, it is random as random data. It's completely random distribution. There's no deviated compression. Now, if you, like, for instance, took a plot file and copied it 20 times and said, look, I have 20 times the amount of space I have. Well, then when a challenge comes in and you do actually have a proof that matches that challenge, it's not like you can respond to that 20 times. It's just you can only respond to it once. So it's like having 20 copies of a lotto ticket. It doesn't make it any more likely to win. It's just 20 copies of the same one.
Yeah. So there's another question. What is the approximate cost difference between a computational storage SSD, CSD, versus a standard SSD of equivalent capacity? A rough estimate will help. So this is a tricky question. There are several different vendors out there today that offer computational storage drives. Each one of them is relying on different technology. Some vendors, their solution of the CSD is based on an SoC. Some is based on an FPGA. Some offer it as an SSD by itself or as a CSD, and some offer it only as a CSD. And it's also a function of quantity, timing, now with all the chip allocation. So as an overall rule of thumb, there is no one way to answer that question. Sorry, but I guess that the really best accurate way to do it is if you have an opportunity to utilize CSD for plotting, is to go and get a quote from one of the CSD vendors, or from a traditional SSD vendor, and compare it. My estimate is that you're probably going to pay a premium, but a very small one that will get waived off when you get the benefits of the compute function.
Yeah, it's really interesting to me too. Like, say for instance, you could find a computational storage device that's 10 to 20% more than a traditional SSD, but you can put it in a system where there's not a lot of compute, or they want it, basically not to use the host compute, and it can just plot in the background and then copy the files over to a hard drive. That's a really cool use case, where even if it's not plotting as fast as like a CPU or DRAM, it doesn't matter because it's like super low energy and just kind of doing it in the background. As I always said, it scales with the number of drives. So say you want to plot 20 times faster, you just put 20 drives in. So it's a kind of interesting way to scale the plotting. And I'm really excited that they put this POC together in white paper. It's really cool.
Yeah, and that also bring another point, that the right way to compare costs is not take the CSD versus SSD and say, okay, this costs 10 and this costs 12. So it's 20% more, and I'm not sure it's worth it. But actually, to look at the entire plan, your system, how many servers, how many racks, and then do the calculation, because it's a combination of CapEx and OpEx, and that's what the SNIA calculator actually is very helpful with, is to try and figure it out ahead of time, and just plug in the numbers that you get from the quote from a standard SSD versus a CSD. All right, next question for you, John Michael. Do you have a comparison from energy efficiency perspective of proof of space and time versus proof of work?
Yeah, we sure do. There's a site that I personally wrote called chiapower.org, which shockingly takes a TCO model And the way that we measure the amount of storage on the Chia network is something called net space. Currently, there's about 35 exabytes of storage on the net space, which is pretty bad, right? If anybody knows, that's like 3,000 10 petabyte racks of the densest racks on the planet. So it's a lot of storage. But the model basically goes through and says, okay, for that amount of storage, what are the average representative people look like that are doing farming on the Chia network, and how much power they consume? What types of hard drives are they using? Looking at the watts per terabytes of these equivalent drives and kind of estimating the power consumption. It's very similar to the model that, like, say, the Cambridge Bitcoin electricity study index basically studies for energy consumption and proof of work. I've read, I've worked with the guys from Ditch Economist and some of the other websites that do these power assumptions for proof of work. And so I've tried to use kind of a similar methodology to that. But go if you want to read a little bit more about how we calculate that. It's called chiapower.org.
All right, another question, this time around RDMA. So assuming future tech of RDMA over converge Ethernet, the ROCE, assuming plotting will not need such a high bandwidth and lower latency. So I guess it's for you, John Michael. What do you think?
Well, there's so I think one of the things I mentioned is there's lots of ways to do like, if there are excess resources like cloud resources to do this plotting, then that's awesome. But the big problem you run into when you start doing this is like moving lots of data around. Like, anybody who's used cloud services, like, when you start moving hundreds of terabytes of data, it's like, these are really hard problems from a network perspective. So either you have doing it local, where you have, bounding it by the storage in the rack and the storage interfaces within the rack and the servers and the DRAM, or, you don't use that. You use a network service, and then you use somebody else's hardware, then it's very inexpensive, or you use it somewhere, like in this example, where there's like low latency or high bandwidth access to a network. Well, then you could do the plotting somewhere else and transfer it over. But yeah, it's always there's not like a one size fits all thing. I think I think people find that doing it locally is most common, because just a lot of moving that much data around in the network right now, especially in consumer type grade networks, is not so easy. So.
Yeah, and that's where computational storage becomes very handy. That reduction in data movement translate to efficiency. Any more questions?
Feel free, come on. I'm sure we have a few more questions.
Maybe not. Well, thank you all for joining. The recording of this webinar will be available through SNIA. You're probably going to get an email with a link. It will be available on the SNIA CMSI website. Thanks again for joining, and have a good rest of your day, evening, night, wherever you are.
Thanks, guys. Yeah, don't forget to rate this on Bright Talk, and we will post it to the SNIA YouTube for folks that aren't on Bright Talk, so they can have access. So,
thank you.
Yeah, thanks again. And feel free to reach out to me if you have any questions about proof of space and time and Chia, JM at Chia. So, thanks, guys.
Thank you.